Albert Einstein. Chapter 1. A small town boy with big dreams. I, Albert, was born in a town called Ulm, Germany, in the year 1879. It wasn't a big city, but it had everything we needed. The streets were made of cobblestones, which were like small, round rocks all stuck together. Our neighbors were friendly, and we always said hello when we saw each other. My family wasn't the richest, but we had enough food to eat and a warm bed to sleep in. My dad, Hermann, was an engineer. He liked to build things and fix things. He could take apart a clock and put it back together again without any trouble. My mom, Pauline, was a very kind person. She loved to cook and always made sure we had delicious meals on the table. From a young age, I loved puzzles and figuring things out. Even as a little boy, I wasn't happy just playing with toys. I wanted to understand how they worked. For example, I had a wooden train with square wheels. It wouldn't roll very well, and that made me curious. Why couldn't it go fast like the real trains I saw puffing smoke outside my window? I took it apart, trying to see if I could fix the wheels. My parents never got mad when I did this. They knew I was just trying to learn. One of my favorite things was a compass my dad gave me when I was 5 years old. It was a small, round object with a needle inside. No matter which way I turned it, the needle always pointed in the same direction, north. This tiny thing filled me with wonder. How could something always know where north was? I carried it everywhere, even to bed sometimes. School wasn't always my favorite place. The teachers wanted us to memorize things, like long poems and lists of dates. This wasn't very interesting to me. I preferred asking questions and thinking about things on my own. Sometimes, the teachers would get frustrated because I wouldn't just do what they said. But my parents always told me it was okay to be curious and ask, why? They said that's how people learn new things. One day, when I was about 7 years old, my dad brought home a strange object. It was a flat, round plate with a needle sticking out in the middle. He told me it was a compass card, and it could be used to navigate on ships. He explained that by looking at the stars and using this compass card, sailors could find their way across the big ocean, even when they couldn't see land. This story sparked my imagination. I spent hours looking at picture books about ships and sailors, dreaming of faraway places and the mysteries of the sea. Another thing I loved was building things. I would use blocks, sticks, and anything else I could find to create little towers and structures. Sometimes, I would even take apart old toys and use the pieces to build something new. My parents encouraged this curiosity. They helped me find tools and materials, and they even helped me build some of my creations. Looking back, I can see how my early life in Ulm shaped who I became. The cobblestone streets, the friendly neighbors, the love of my parents, and the freedom to explore and ask questions. All these things helped me develop a curious mind and a desire to understand the world around me. It wasn't always easy, but it was a wonderful adventure that set me on a path of lifelong learning and discovery. Chapter 2. Moving on and finding my path. When I was 15 years old, my family made a big decision. We were going to move to a much bigger city called Munich. This was scary for me at first. Ulm was my home, and I knew everyone there. Munich seemed like a giant, unknown place with lots of people and buildings I didn't know. It was like stepping off a small boat onto a vast ocean. Saying goodbye to my friends and neighbors was hard. We promised to write letters to each other, but I knew it wouldn't be the same. However, my parents were excited about the move. They believed Munich would offer more opportunities for me, especially for my education. Munich was definitely different from Ulm. The streets were wider and busier, filled with cars and horse-drawn carriages. There were tall buildings everywhere, and it seemed like there were always people rushing around in a hurry. It took a while to get used to all the noise and activity, but Munich also had some amazing things to offer. One of the first places I explored was the library. It was a huge building with rows and rows of books that seemed to stretch on forever. There were books on every subject you could imagine, from history and geography to science and stories. I spent hours wandering through the library, discovering new worlds and learning about amazing things. Another exciting discovery was the Deutsches Museum. It was a place filled with all sorts of machines and inventions, from old clocks and telescopes to steam engines and printing presses. I could spend all day exploring these exhibits, marveling at human ingenuity and the power of technology. School in Munich, however, wasn't much better than in Ulm. The teachers still focused on memorizing facts and dates, which I found boring. I craved a deeper understanding, a way to connect the dots and see how things work together. I preferred to ask questions and discuss ideas, but the teachers often discouraged this. One day, a new student named Max joined my class. Max was different. He was also curious and loved to ask questions. We quickly became friends and spent our free time talking about science, philosophy, and anything else that sparked our interest. We even started a small club where we could discuss these topics with other curious students. One evening, while reading a book on electricity, I came across a story about Benjamin Franklin and his famous kite experiment. The idea that lightning was just a giant spark of electricity was mind-blowing. It made me realize how much we still didn't know about the world around us. There were so many mysteries waiting to be solved, and I wanted to be a part of that exploration. Another turning point came when I discovered the works of Isaac Newton. Newton was a brilliant scientist who had developed laws of motion and gravity. Learning about how gravity held planets in orbit and caused objects to fall to the ground was fascinating. For the first time, I felt like I was starting to understand some of the basic rules that govern the universe. However, the more I learned, the more questions I seemed to have. It was frustrating at times, but also exciting. It fueled my desire to learn even more and find answers to these mysteries. Despite my struggles with school, my parents continued to support my curiosity. They encouraged me to read books on my own and even bought me a basic chemistry set. I spent hours mixing chemicals and observing their reactions, trying to understand the basic principles at work. By the time I was 17, I knew that the traditional school system wasn't right for me. I needed a place where I could learn and explore freely, a place that encouraged independent thinking and questioning. After a long discussion with my parents, we decided that I should leave school and find a place that could better nurture my curiosity and passion for science. It was a big decision, and I was a little scared, but I knew in my heart that it was the right thing to do. Leaving Munich and my family behind was tough, but I was determined to find my path and pursue my dream of understanding the universe. Chapter 3: University Days and First Discoveries. Saying goodbye to Munich and my family wasn't easy. Leaving the familiar streets and the comfort of home filled me with a mix of excitement and nervousness. But the desire to learn and explore was stronger. With the support of my parents, I set off on a new adventure, finding the right university. Finding the perfect fit wasn't simple, Traditional universities seemed more focused on following established rules than encouraging independent thinking. I craved a place where professors challenged students to question, to think outside the box, and to explore new ideas. Fortunately, my search led me to a special school in Zurich, Switzerland, called the Swiss Federal Institute of Technology. It was different from the universities I had encountered before. Here, the professors were more like guides on a journey of discovery, encouraging students to think for themselves and explore their own questions. The focus was on understanding the why behind things, not just memorizing facts. The moment I stepped foot on campus, I felt a sense of belonging. Students from all over the world gathered at Zurich, each with their own unique perspective and passion for learning. I quickly made friends with other curious minds, some of whom shared my fascination with science and mathematics. Together, we spent countless hours discussing complex theories, solving challenging problems, and pushing each other to think deeper. One of the most important people I met during my university days was Maliva Merrick. Maliva was a brilliant young woman who was also studying physics. She wasn't afraid to challenge my ideas, which actually helped me think more critically about my own work. We not only shared a love for science, but also developed a strong emotional connection. After graduation, we married and embarked on a journey of discovery together. During my university years, I devoured books and lectures on various scientific subjects, from physics and mathematics to philosophy and engineering. Each new concept was like a piece of a puzzle, helping me to understand the bigger picture of how the universe worked. But it wasn't all smooth sailing. There were times when complex theories felt like a tangled mess and solutions seemed impossible to find. Frustration would set in, making me question my abilities. However, Maliva's unwavering support and my own determination kept me going. I learned that the path to discovery is rarely a straight line. It's often filled with twists, turns, and roadblocks. Then, one day, while studying about magnetism, a simple question sparked a series of thoughts that would eventually lead to a groundbreaking discovery. Magnets have a special power to attract certain objects, like iron or steel. But what if I moved really, really fast? Would the magnet still behave the same way? This seemingly simple question opened a door to a whole new way of thinking about space, time, and the universe. For years, this question gnawed at me. I spent countless hours reading everything I could find about magnetism, motion, and the nature of light. I even started to visualize myself traveling at incredible speeds, imagining what the world might look like. Slowly, a new theory began to take shape in my mind. I called it the theory of special relativity. This theory challenged the way we understood time and space. According to special relativity, time wasn't the same for everyone. It could actually slow down or speed up, depending on how fast you were moving. It was a radical idea, and at first, many scientists didn't believe it. But I was convinced of my calculations, and I knew time would prove me right. Developing this theory wasn't just about equations and calculations. It was about using my imagination and thinking outside the box. It was about questioning what we thought we knew and daring to explore new possibilities. This was the true essence of learning at the Swiss Federal Institute of Technology, and it was a lesson that would stay with me throughout my life. While university life provided a stimulating environment for learning and discovery, it wasn't all about studies. Zurich offered a vibrant culture and beautiful scenery. On weekends, Maliva and I would often explore the surrounding mountains, taking long walks and enjoying the fresh air. These moments of quiet reflection helped me recharge and gain new perspectives on the scientific problems I was tackling. Looking back, my university days in Zurich were a transformative period. It was a time of intense learning, deep friendships, and the birth of a groundbreaking idea. It was the foundation upon which I would build the rest of my scientific journey. Chapter 4. The Theory of Special Relativity Explained. Imagine you're on a train traveling very, very fast. So fast, it's almost impossible to believe. Now, picture a friend standing on the platform outside, waving goodbye. According to my theory of special relativity, things might seem a little different for you and your friend. Here's the surprising part. Time wouldn't tick by at the same rate for both of you. For you, on the fast-moving train, time might seem to slow down a little bit. It might feel like your watch is ticking slower compared to your friend's watch on the platform. This might sound crazy, but it's a consequence of special relativity. Think of it like this. Imagine a light ray traveling from one end of the train to the other. For your friend on the platform, the light ray has a longer distance to travel because the train is moving. But for you, on the train, the distance seems shorter because you're moving with the train. To make the trip in the same amount of time, according to the theory, something has to give. In this case, it's time itself. For you, time seems to slow down just a tiny bit to compensate for the shorter distance the light ray travels from your perspective. Now, this doesn't mean you'd actually age slower on a fast train. The difference in time would be incredibly small, almost impossible to measure with everyday clocks. But for objects traveling at incredibly high speeds, like particles in space, this tiny time difference can become significant. Another surprising part of special relativity is the idea of length contraction. Imagine the train itself. For your friend on the platform, the train will appear shorter than its actual length. This is because the train is squished a little bit in the direction it's moving. Again, for very high speeds, this effect becomes more noticeable. But for everyday objects and speeds, the change in length is too small to see with our naked eyes. These ideas, time dilation, slowing down, and length contraction, were the cornerstones of my theory of special relativity. It challenged the way we understood the universe and the basic rules of space and time. Until then, most people believed that time flowed at the same rate everywhere, no matter what. Special relativity showed that time wasn't absolute, but could be relative depending on your motion. Developing this theory wasn't easy. It took years of thinking, calculating, and questioning everything I thought I knew. Many scientists I admired at first didn't believe my ideas. They thought it was impossible for time to change just because you were moving, but I was confident in my calculations. I knew I wasn't just making things up. The math all pointed towards this new understanding of space and time. Slowly, through experiments and further research, other scientists began to see the evidence supporting my theory. However, explaining these complex ideas to people who weren't scientists was even more challenging. Imagine trying to explain why time might slow down for someone on a fast train. It required using simple examples and analogies to help people grasp the basic concepts. One way I like to explain it was with a race between two runners. Imagine two twins, named Alex and Ben. Alex stays on Earth, while Ben takes a super-fast spaceship for a journey to a distant star and back. According to special relativity, when Ben returns to Earth, he would be a tiny bit younger than Alex. This might seem strange, but it has to do with the different paths they took. Ben's journey involved traveling at a very high speed. which, according to the theory, slows down time for him compared to Alex, who stayed on Earth. Of course, these are just simplified examples to illustrate the core ideas. Special relativity is a complex theory with many equations and technical details. But the basic message is that our understanding of space and time isn't as simple as we might think. There's more to the universe than meets the eye, and special relativity opened a door to a whole new way of looking at it. The theory of special relativity wasn't just about time travel or spaceships, although it has inspired many science fiction stories. It had real-world applications in various fields, from the development of GPS technology to our understanding of subatomic particles. It showed that the universe is filled with fascinating phenomena that we're only just beginning to understand. Special relativity was just the beginning of my scientific journey. It sparked a fire within me, a desire to explore the universe's deepest mysteries. And who knows, maybe one day, we'll even discover ways to travel at speeds that truly make time slow down. Chapter 5. Recognition, Rejection, and a Powerful Idea. The theory of special relativity slowly began to spread through the scientific community. At first, it was met with skepticism. Many scientists found the ideas of time dilation, slowing down, and length contraction too radical to believe. They questioned how something as fundamental as time could change based on your motion. However, there were also scientists who were intrigued by my work. They saw the potential of special relativity to revolutionize our understanding of the universe. They carefully examined my calculations and the logical reasoning behind them. Slowly, evidence started to support the theory. Experiments conducted with high-speed particles confirmed some of the predictions made by special relativity. This growing acceptance led to a change in my life. I started receiving invitations to speak at conferences around the world. Scientists from different countries wanted to hear about my theory and discuss its implications. This shy boy who loved puzzles was suddenly thrust into the spotlight. It was an exciting time, but also a bit overwhelming. Traveling the world and giving presentations wasn't something I was used to. However, I knew it was important to share my ideas and explain them to the best of my ability. One of the challenges of being a famous scientist was dealing with journalists and the media. They often wanted to sensationalize my work, focusing on the most outlandish aspects of special relativity like time travel. While the theory opened up possibilities for exploring the universe in new ways, actual time travel wasn't something I predicted. It was important to clarify these misconceptions and explain the science accurately. During this time, I also continued my research at various universities in Switzerland and Germany. University life provided me with the freedom and resources to explore new ideas and delve deeper into the mysteries of the universe. One day, while working on a completely different problem, a simple equation popped into my head. It was a powerful equation that seemed to connect two seemingly unrelated concepts: mass, the amount of matter in an object, and energy, the ability to do work. The equation was short and elegant: E equals mc squared. This simple equation, E equals mc squared, expressed a profound truth about the universe. It showed that mass and energy are actually different forms of the same thing. Just like water can exist as ice, liquid, or vapor, depending on the temperature, mass and energy can transform into each other under certain conditions. The equation had far-reaching consequences. It suggested that even a tiny amount of mass could be converted into a tremendous amount of energy. This principle became the foundation for nuclear power and, unfortunately, also for the development of atomic bombs. The idea of something as destructive as an atomic bomb troubled me deeply. I had always believed science should be used for good, not for destruction. The world was entering a new era, one filled with both incredible potential and terrifying threats. The rise of Adolf Hitler in Germany also had a profound impact on my life. As a Jew, I no longer felt safe in my home country. My work on the atom was being used by the Nazi regime, something I vehemently opposed. In 1933, I made the difficult decision to leave Germany and seek refuge in the United States. Leaving my homeland and friends was heartbreaking, but it was necessary for my safety and the continuation of my work. The United States offered a new beginning, a place where I could continue my research freely and contribute to the advancement of science for the betterment of humanity. This chapter of my life was a roller coaster of emotions. The recognition of special relativity brought fame and excitement. However, it also raised concerns about its potential misuse. The development of the E=mc² equation opened up new scientific possibilities, but also the terrifying reality of nuclear weapons. Finally, the rise of Nazi Germany forced me to leave everything behind and seek refuge in a new country. Despite the challenges, I remained optimistic about the future. Science had the potential to solve some of humanity's greatest problems, but it required responsibility and a commitment to using knowledge for good. Chapter 6: A World in Motion and a Heavy Heart. The world was changing rapidly in the early 1900s. It felt like everything was moving faster, just like the ideas in my theory of special relativity. New technologies were emerging all the time, like airplanes that could fly across vast distances and radios that allowed people to hear voices from faraway places. It was a time of great progress, but also a time of growing tension. One of the biggest changes I witnessed was the rise of nationalism. Countries became more focused on their own interests, often at the expense of others. This led to a sense of competition and suspicion between nations, which ultimately contributed to the outbreak of World War I in 1914. The war was a terrible tragedy. Millions of young men died fighting in trenches, and families were torn apart. The horrors of war filled me with sadness and a sense of helplessness. Science and technology, which were supposed to improve our lives, were now being used for destruction on a massive scale. Meanwhile, my own life was in a state of flux. In 1914, I moved to Berlin, Germany, where I accepted a prestigious position at a leading scientific institute. However, my time there was overshadowed by the war and growing social unrest in Germany. As a Jew, I began to feel increasingly unsafe. The rise of Adolf Hitler and the Nazi Party fueled a climate of hatred and discrimination. My work on the atom, and particularly the E=mc² equation, was being used by the Nazi regime for their own purposes. This went against everything I believed in. Science was meant to help humanity, not destroy it. In 1933, when Hitler became Chancellor of Germany, I knew I had to make a difficult decision. Staying in Germany meant putting myself and my family at risk. It also meant being associated with a regime that was using science for evil. With a heavy heart, I decided to leave Germany once again. This time, I sought refuge in the United States. It was a new country with a different culture, but it offered a safe haven for me and my family. The journey to America was long and uncertain. Leaving behind my friends, colleagues, and everything familiar was a painful experience. However, I knew it was necessary for my safety and the freedom to continue my scientific work. The United States was a welcoming place in many ways. There was a spirit of optimism and a belief in the power of science to solve problems. I was offered a position at the Institute for Advanced Study in Princeton, New Jersey. It was a small research institute with a focus on fundamental science, which was a perfect fit for me. Despite the fresh start in America, the shadow of war and the dangers of science misused still lingered. World War II erupted in 1939, engulfing Europe in another bloody conflict. The news of the atrocities committed by the Nazis filled me with horror. It was a constant reminder of why I had left Germany and the importance of using science for the betterment of humanity. The war also led to the development of the first atomic bomb in the United States. This was a sobering realization. My own E=mc² equation had played a role in creating this devastating weapon. While it was crucial to ensure the Nazis didn't develop the technology first, the thought of the bomb being used on innocent people filled me with dread. The bombing of Hiroshima and Nagasaki in 1945 confirmed my worst fears. These attacks brought an end to the war in the Pacific, but at a terrible cost. The destruction and suffering caused by the atomic bombs were immense. It was a stark reminder of the destructive power of science when used without ethical considerations. This chapter of my life was marked by immense changes and profound challenges. The world was in turmoil, and science, which held so much promise, was being used for both good and evil. Leaving Germany and starting anew in America offered a sense of hope, but the scars of war and the misuse of knowledge remained a constant source of worry. Chapter 7: Never Stop Thinking. A Life Dedicated to Science. Settling into life in America was a gradual process. Princeton was a quiet town compared to the bustling cities I had lived in before, but it had a charm of its own, with beautiful surroundings and a strong sense of community. The Institute for Advanced Study offered an intellectual environment that stimulated my mind and allowed me to focus on my research without distractions. Despite the peace and quiet of Princeton, the world outside was still a troubled place. The aftermath of World War II left deep scars, and the Cold War created a new kind of tension between nations. This only reinforced my belief in the importance of science as a force for good, a way to solve problems and improve the lives of people around the world. During these years, I continued my research on various scientific problems. One topic that fascinated me was the nature of gravity. Gravity is the invisible force that keeps us grounded and holds planets in orbit around the sun. We all experience gravity every day, but until then, no one had a truly complete understanding of how it worked. My previous theory, special relativity, focused on motion and space-time. Gravity, on the other hand, dealt with a different aspect of the universe, the warping of space and time by mass and energy. Imagine a bowling ball placed on a trampoline. The ball would create a dent in the fabric of the trampoline, and other objects rolling nearby would be pulled towards the dent. In a similar way, I theorized that massive objects like stars and planets warped the fabric of space and time, creating a gravitational pull that attracted other objects. This theory became known as general relativity. It was a complex theory, even more complex than special relativity. It involved a lot of advanced mathematics and challenged our understanding of space and time in even more profound ways. Developing general relativity took years of thought, calculations, and revisions. There were times when I felt stuck, unable to find the missing piece of the puzzle. But I never gave up. I believed that there was a simple and elegant explanation for gravity, and I was determined to find it. Finally, after years of work, I arrived at a set of equations that describe the behavior of gravity according to my theory. These equations were like a recipe for understanding how gravity worked. They could be used to predict the motion of planets, the bending of light by gravity, and even the existence of black holes, incredibly dense objects in space with such strong gravity that not even light can escape them. General relativity wasn't readily accepted by the scientific community at first. It was a radical new idea that challenged the established way of thinking about gravity. However, over time, evidence began to support the theory. Astronomical observations confirmed the predictions made by general relativity, such as the bending of light by the sun's gravity. This growing body of evidence slowly convinced more and more scientists that general relativity was indeed the correct explanation for gravity. However, explaining complex scientific ideas to the general public remained a challenge. General relativity involved concepts like curved space-time and black holes, which were difficult to grasp for people without a scientific background. I use simple analogies and metaphors to try and explain the basic ideas. For example, I might compare the curvature of space-time to a bowling ball on a trampoline, as mentioned earlier. While some of the details of general relativity might be hard to understand, the core message is quite simple. Gravity isn't just a force pulling things down. It's a warping of space and time caused by mass and energy. This new understanding of gravity had profound implications for our understanding of the universe on a grand scale. Beyond general relativity, I also explored other areas of science during my time at the Institute. I delved into the world of quantum mechanics, a theory that deals with the behavior of matter at the atomic and subatomic level. While quantum mechanics seem to contradict some of the principles of special relativity, I believe there must be a way to reconcile these two seemingly opposing theories. The search for a unified theory that explained both the large-scale universe, general relativity, and the microscopic world, quantum mechanics, became a lifelong pursuit for me, though a solution remained elusive. One of the joys of working at the Institute was the opportunity to interact with other brilliant minds from various scientific disciplines. We would often have lively discussions about new discoveries and challenging problems. These intellectual exchanges stimulated my thinking and helped me see things from different perspectives. As I got older, I became increasingly concerned about the future of humanity. The threat of nuclear war loomed large during the Cold War, and the misuse of science for destructive purposes worried me deeply. I believed scientists had a responsibility to speak out against the misuse of their discoveries and advocate for the peaceful use of science and technology. I used my public profile to promote peace and international cooperation. Chapter 8. Looking back and looking forward. Life is a fascinating journey, full of surprises and challenges. As I look back on my years, I realize how lucky I was to have been born with a curious mind. Every question, every puzzle, led me down a path of discovery. It wasn't always easy. There were times of doubt and frustration, when answers seemed unreachable. But with hard work and a little bit of imagination, those moments of struggle would give way to breakthroughs. One of the most important lessons I learned is the value of asking questions. Never be afraid to say, "I don't know," or "Why is that so?" The best way to learn is to be curious and explore freely. Don't be afraid to be different. Sometimes, The most important ideas come from people who think outside the box. The world is a much more complicated place than the one I grew up in. Technology has changed everything, and the challenges we face are even greater. But I believe that, just like before, the key to solving these problems lies in curiosity and collaboration. Science is not just about equations and experiments. It's about a way of thinking, a way of questioning the world around us. By working together, using our knowledge and imagination, we can create a better future for everyone. So, to the young readers out there, I leave you with these words: never stop asking questions, never stop learning, and never stop dreaming. The universe is full of wonder, and it's up to you to explore it.